So several people told me the end was a bit fast in the last lecture, so I'll go back to what I was saying and do it a bit slower. Actually, I made some sort of improvised decisions to change the order I was doing things, and then I realized really I need to take a step back and explain some more basic things first. Okay, so I was in the middle of telling you about why the triangle condition implies the mean field critical behavior. Before returning to that, though, let me start by telling you about some important basic inequalities for percolation. This is known as correlation inequalities. Okay, and for percolation, there are essentially two very important correlation inequalities. So the first one is what's called the Harris FKG inequality. And I should say both of these inequalities I'm about to write down, they're not really anything about percolation, they're just about IAD coin flips, IAD Bernoulli random variables. They're just factor, in other words, about measures on the product measures on the hypercube. Okay, so the first one, the Harris FKG inequality, says that if A and B are increasing events. So remember, an event is said to be increasing if its indicator function is increasing, i.e. if you change some of the coins from being tails to heads and the event already held, then it will continue to hold after you make more heads, more coins heads, or in context of percolation, if you say more edges are up. Okay. So it says if the Harris FKG says if you have two increasing events, A and B, then the probability that A and B both hold for any value of P is at least the product. Okay? And in fact, this holds for any product measure on the hypercube, not just they don't have to all have, you don't have to have the same probability, you know, for every bit. Okay? So the reason it's called this is that this inequality is really just due to Harris, who introduced this in the context of his proof that I mentioned earlier, that there's no percolation on the square grid at p equals a half. The reason it's often called the FKG inequality is that F, K, and G, which are Fortune, Castelline, and Ginebra, gave a sufficient condition for this inequality to hold for non-product measures, called the FKG lattice condition, which is very influential, and as a result, this kind of inequality is often known as the FKG inequality. Okay, so it just says that, you know, if you have two increasing events, whether they, any two increasing events are positively correlated. Okay, now in fact, of course, this also holds more generally if you just have any two increasing functions, then they're also positively correlated. It's not really anything to do with the fact that they're indicator functions. Okay, so that's our first basic correlation inequality. Okay, and by the way, of course, this also holds if both the events are decreasing, because just by symmetry, I mean, you know, you can flip the status of all the edges and it becomes equivalent. Okay. Yeah.
Just comment that Ginebra was at Orsay, was physicist at Orsay.
Okay, I didn't know that. Yeah, thank you. Okay. So the other really important inequality for us is the BK inequality. So B and K are Vandenberg and Keston. Okay, and the BK inequality is sort of a complementary inequality to Harris FKG. So Harris FKG captures, in some sense, the way in which product measures are positively associated, and the BK inequality captures a complementary sense in which product measures are also negatively associated. Okay, so it's a bit more difficult to set up what this inequality is. So the first thing is, let's say that A is an event. Okay, so okay, suppose we have some configuration that belongs to A. Okay, so we say a set of edges W is a witness for the fact that omega belongs to A, if for all omega prime, any other configuration with the same restriction to W, say if every other configuration with the same restriction to W also belongs to A. So in other words, just knowing the configuration on the set W is sufficient to tell you that the configuration belongs to the set. Okay? So for example, you can always take W to be the entire edge set. That's always a witness. If omega belongs to A, then the entire edge set is always a witness for the fact that it belongs to A. Okay? But for example, if A is equal to the event that X is connected to Y, then any open path is a witness. Okay, because knowing that that open path is there, if I change the configuration, that information about what the configuration looks like on that set is sufficient to determine that you belong to the event. And notice that this open path, it certainly depends on the choice of the configuration, and it may also be highly non-unique. I mean, of course, if I have any witness, I can always add more edges to the witness, and it continues to be a witness, for example. Okay. So, given A and B, two events. By the way, by an event, I just mean a measurable set, right? Which, of course, when E is finite, this is just any subset. Given two events A and B, we define this notation, a circ B, which we call the disjoint occurrence, to be the set of omega such that omega belongs to A and B, and there exist disjoint witnesses and W2 for these two inclusions. Okay, so hopefully that makes sense as a definition. And of course, I really want to stress that these choices of witnesses can be highly non-unique, right? So in particular, this doesn't mean that any witness for omega belonging to A is disjoint from any witness belonging to that omega belongs to B, right? It's just saying you can find a witness for omega in A and a witness for omega in B that are disjoint, right? That's the definition of this set. Okay, and the BK inequality says that if A and B are increasing, then, and again, this is really a fact about any product measure, so different edges can have different probabilities, but let me just write it this way. The probability of the disjoint occurrence is bounded by the product. Oh, sorry. Okay. Notice, by the way, that this also makes sense. A and B could be the same, right? The disjoint occurrence of A and A is a perfectly well-defined thing that is not the same thing as just A. Okay. And again, this is complementary to FKG in that the FKG inequality gives you the bound in the other direction when you just look at the intersection. Okay? So it's like if you require that A and B just both hold, that's more likely than if they were independent. But if you require that they hold for different reasons, which you can kind of think of what the meaning of this thing, then it's less likely than if they were independent. Okay? So, this is one of the key tools in percolation that you can play off these two different inequalities that again capture the sense in which the product measure is kind of positively associated and kind of negatively associated, depending on how you think about things. Okay. Now, in fact, this inequality is this one. I mean, not the second one. This is also true for arbitrary events. This is called Reimer's inequality. So the probability of the disjoint occurrence is always bounded by the product. That's actually a much harder thing to prove, though, and in practice we normally use the BK inequality. So the community has maintained the tradition of usually referring just to the BK inequality when that's what's being used. I should mention that the case where each of the events is not arbitrary but is the intersection of an increasing event and a decreasing event is significantly easier to prove than the general Reimer's inequality. It's sometimes called the Vandenberg-Kasten-Feibig inequality. So we will, I think, actually see some uses of that. But in any case, in fact, this inequality is just always true. I should say all of these things here about the BK inequality, strictly speaking, these are inequalities for events only depending on finitely many edges. This is one of these things that I don't want to belabor too much, so I will sort of use these inequalities without that assumption, and they can always be justified by taking some kind of limit. You can imagine when you have general events, there can be concerns over whether this event is even measurable, right? Because it involves taking some existential quantifier over all subsets and so on. Good. Okay. So one of the most important applications of the BK inequality are the tree graph inequalities of Eisenman and Newman. So in fact, their proof of these inequalities actually predates the BK inequality. They had a different argument that didn't use it, but the standard way to do it now is using BK. Okay, so the tree graph inequalities are a way of bounding what we call k-point functions. So we talked about the two-point function, i.e. the probability x is connected to y. So the k-point function just means if you have k points, you understand what's the probability they all belong to the same cluster. Okay, and so an example of a tree graph inequality is, let's look at the probability that x, y, and z all belong to the same cluster. By the way, I think I'll start using the notation for k-point functions, which is to call this tau. So if I write tau of p and then some variables, it means the probability they all belong to the same cluster. Okay? So the first of the tree graph inequalities is that, again, these are actually things which are true on any graph, okay? And any value of p. Eventually we'll mostly be applying them at or near PC, but they're true always. You can always bound the three-point function by summing over one additional vertex of the product of the three two-point functions, like this. Okay. Now, why is this true? I guess I'll call this theorem. Again, this is due to Eisenman and Newman. Well, let's suppose that we have x is connected to y and to z. Okay, so there's some open path connecting x to y, and there's some other open path connecting x to z. Okay, now what you can do, and of course there could be very many of these paths, but let's just pick two of them. Now, take this second path going from x to z, and consider the last place it intersects the first path. Okay, so in this diagram, that's this point here. Let's call that w. So what you see is, in fact, you have just by deleting this initial segment of the second path, we have this collection of 3 paths from x to w, w to y, and w to z. And these 3 paths are disjoint, right? That follows by the construction because we picked the last place this path intersects this one. Okay? And so what this says is that the events that x, y, and z are all connected to each other is contained in the union over w of the disjointed currents. X is connected to w, disjointly w is connected to y, sorry. Disjointly w is connected to z. Okay, now I only defined the BK inequality in disjointed currents for 2 events, but you know it extends to k events. Okay, and so what you can do is then just use the union bound, right? So the probability of this triple connection, well, it's bounded by the sum over w of the probability of this triple disjointed currents, right? Which by the BK inequality is bounded by, well, for each w it's bounded by this, right? And then I'm just summing them, so I get this inequality. Okay, good. So a consequence of this is that if I look at the second moment, let's say I'm back on Z, I'm doing back on ZD, so it's transitive. You know, these moments don't depend on which point I pick to be the origin. If I look at the second moment of the cluster at the origin, it's bounded by the cube at the first moment. Okay, why is that true? Well, of course, the second moment is nothing other than, right, the sum over x and y of the 3-point function, right? I mean, that's sort of the definition of the second moment, if you like, right? And so if I use this inequality, I get that this is bounded by the sum over x, y, and w of tau p 0w, tau p wx, tau p wy. Okay? But you see, you know, once I fix w, these sum, right, I can just move this sum over x here, this sum over y here, and this is exactly equal to the cube of the first moment. Okay? Good. So one interesting thing that will come up importantly later on is that this inequality is one of the many things where we get a general inequality. Like before, we had that the derivative of the first moment is always bounded by the square of the first moment, right? And there are many of these inequalities, again, that are of the correct order in high dimensions, but not in low dimensions. And actually, many of these characterize mean field behavior. So it turns out this is one of those things where actually, if you know that the second moment is always of the same order as the first moment cubed, that's actually one of the many equivalent ways of characterizing mean field critical behavior. Okay. In fact, maybe I'll just mention.
So essentially, it says that if these 3 points are correlated, then they have to be correlated with high probability by single path.
Or like order 1, yeah, exactly.
So is it related? So for Ising model, the criticality is like 2 paths don't intersect, which gives this dimension 4, and then 3 paths. I guess is it related to?
Yeah, it's. Yeah, it is related to that. It's essentially, I mean, we'll look at more of these tree graph inequalities, but basically for percolation, when you write down these kind of tree graph inequalities, they involve trees with internal degrees 3. And when you do similar things for self-voiding walk or the Ising model, you get trees with internal degree 4. And that's related to why you get 4 versus 6, or 6 versus 4 for the different critical dimensions. Yeah, so I'll just mention, yeah, so one way you can think of this is why this, again, might be one of the many things that characterize this high-dimensional behavior is that, you know, in general, this point where the 3 paths meet might be highly non-unique, right? I mean, they might actually, you might have some cluster that doesn't look anything like a tree, and there are actually a huge number of choices in the cluster for where this you could take this triple point to be, which would basically mean that this union bound that you do is not of the correct order. Okay. There's of course another thing that could be giving you the wrong order, which is just the use of the BK inequality, right? So you know in the BK inequality you basically say when you try to form these 3 arms, like these 3 paths coming off, that's always harder than just forming one path coming off and cubing it. But you know, in low dimensions, these 3 things, they're really competing for space with each other, and it's actually much harder to have an additional path than to have the first one. So there are a number of reasons why this bound should not be of the correct order in low dimensions. Okay, so I'll just mention one cute thing regarding this, which I proved, I think some years ago now, I'm not sure, which is that in fact, the derivative is always bounded below by a constant times the ratio of the second moment to the first moment. So, so in fact, if this bound is actually the right order, then that's another way of getting this this lower bound on the derivative. Anyway, that's just an aside. So, okay. Okay, so, you know, I said tree graph inequalities, and that's because, you know, this bound that I just wrote down is just the first bound in a family of natural further inequalities. So what about if you look at the 4-point function? Okay, well, we can try doing the same thing again, right? So we have our 4 points, and we know we can find these 2 disjoint, these paths meeting at these 3 disjoint paths meeting at some additional vertex. Let's call it A. Okay, and then we can do the same thing. We find a path to W. You know, and you find the last place that it intersects the first few paths you drew. In this case, it would be this, right? And then you have a similar thing. So you have this disjoint occurrence. You now have 1, 2, 3, 4, 5 paths, right? And you have these 2 internal vertices. So you would get that, you know, you can write this 4-point function as a sum over where these internal vertices are, and then you have a product of probabilities. Now, of course, the additional subtlety is that when we did it for 2 points, we always got the same tree, right? We just had this one internal vertex and had a path from X to there to Y, there to Z. In this case, we can actually get more than one tree, right? You know, maybe this final path didn't look like this. Maybe it looked like, or maybe it just looked like this, right? And then this second internal vertex is here. Right, or maybe it intersects this tree for the last part here. Okay, so in fact, what happens in this case, there are 3 different combinatorial trees that you have to sum over. Right, they're the ones that look like. Actually, they all look the same as a tree. Actually, it just depends which vertices are labeled what. Right, so it could be Y, Z, W. It could be Y, W, Z. Or it could be W, Z, Y. Okay, so when you form these tree graph inequalities, you have to sum over these 3 distinct isomorphism classes of trees that might appear. Okay, so in particular, if you take this bound on the 4-point function and then use it to deduce a bound on the 3rd moment, what you get now is that the third moment is bounded by 3 times the first moment to the power 5. Okay? Why is it 5? It's because there are 5 edges in this tree. Why is it 3? It's because there are 3 isomorphism classes of binary trees with labels, leaves labeled 0 through 3 and with internal vertices that are unlabeled. Okay? In general, well, you get something very similar. You get that you can bound the k-point function for any number of variables here. You have to sum over isomorphism classes of these rooted labeled trees whose leaves are they're binary, and the internal vertices always have degree 3. The leaves are labeled 1 through k minus 1, I guess. And you have to sum over those. So in particular, if you look at the pth moment, I apologize for the 2 different p's, but let me say case moment. If you look at the kth moment, this is a small k though, right? It's okay. What you get is, this is the prefactor, 2k minus 3 double factorial. That means you multiply all the odd numbers from 1 to 2k minus 3, right? Which is exactly the number of isomorphism classes of these leaf-labeled binary trees, which is a nice exercise if you haven't seen it before. To the power, the first moment, to the power of the number of internal, the number of edges of these trees, which is 2p minus 1. Yes, sorry. Okay. Good. All right, so
is it possible to have inequalities with using other moments than the first one on the right?
Yeah, in fact, that's something that will probably come up next week. Okay. Actually, there are some interesting problems about how to do that optimally, okay. but I'll come back to that later. Yeah, these inequalities are very important. They have a lot of applications. Before telling you about some of the other ones, let's go back to what I was talking about this morning, which was how the relevance of the triangle condition for getting mean field behavior. Okay. Right. So earlier I was saying how we have this triangle which we define to be, and I'll use my tau notation now. X, y, tau p, why not? So actually, maybe before saying this, when we're talking about the tree graph inequality here, we were doing these pictures of the different trees and so on. And it's actually very useful for many things to actually express sums in terms of graphs like this. So this is what's known as diagrammatic notation. It's related to Feynman diagrams in physics. So for example, we can define the susceptibility to be this diagram. What does that mean? It means the white vertex, the unshaded one, is the one that's fixed. Of course, it doesn't matter what you fix it to, you'll get the same value. And shaded vertices are summed over, and edges denote the two-point function, right? So this notation just means you sum over the one shaded vertex, which you can call whatever you want. Of course, it's a dummy variable of the two-point function, just the two-point function. You could consider the bubble diagram, which would be the sum of the square. Right. You can consider the triangle diagram, which is, of course, the one that we have here. Right? And the tree graph inequality is basically saying, well, if we look at the second one, for example, it says, sorry, the one for the second moment is just saying that the second moment is bounded by this diagram. Okay, hopefully that notation makes sense. Sometimes you'll want to use this notation where you have more than one unshaded vertex to denote more than one free variable. So for example, I mean, one thing you could just denote the two-point function by this. Of course, you would have to label them if you wanted to give these variables names.
Can we write the left-hand side of the tree graph inequality as a diagram as well?
What do you mean? Oh, the second moment? You'd need to introduce some additional diagrammatic notation for that. I mean, it's natural. One does sometimes do that. You might. This would be like a sort of hypergraph type, right? It's the three-point function is like a hyperedge. So, yeah, you can do it. You would just need to have some visual rules for how you draw hyperedges. Yeah.
Sorry, with the domination about the square, isn't the black vertex at the middle? Or? It's really this picture? Or?
Well, okay, yeah, it is this picture, but one thing is if you only have one unshaded vertex, it actually doesn't matter which one it is.
Mass transport?
Yeah, this is, again, this mass transport thing, which is, again, it's like Tonelli's theorem, if you like. If you have one of these diagrams and it has a single unshaded vertex, then you can change which one is the single unshaded vertex that's pinned to the origin. You don't change the value of the diagram. So actually, like when you use this, you very often want to actually make the pinned one be in the middle because it's more symmetric, something like that. It doesn't make any difference to the value that you get. Okay. Good. Okay. So why? Let's go back to why this triangle diagram is relevant for getting the mean field critical behavior. So this morning I started talking about this idea of the coupling of the two configurations, right? So let me go through that again because I think I rushed it a bit. So one way you can couple, let's say take K to be the cluster at the origin and K tilde Y to be an independent cluster of Y. Okay? So the claim is that I can couple this pair with the actual configuration so that, well, K just is the cluster at the origin. And if Y is not in this cluster, then the actual cluster KY is contained in this independent cluster, and it has the property that in this situation, if X is in the independent cluster then X and Y is not in the cluster at the origin, then X is in the true cluster of Y if and only if there exists a path Y to X in this independent cluster which is disjoint from K. So again, this is this coupling where you say first you sample the cluster at the origin, and then you sample this independent cluster of Y, and then you use the rule that anywhere any edge that got assigned a value by both things, priority is given to the cluster at the origin. Okay? And if you do that, you'll get the correct distribution for the percolation measure. You have to define it on the remaining edges that you didn't sample yet, and it will have this property. Okay? Now, also recall that for the derivative, what we wanted to understand was we had this pair of points that are next to each other, the origin and y, right? And we wanted to look at the expected size of these two clusters given that they're distinct. Okay? Now, of course, I can write that, again, using linearity of expectation as the sum over some additional points x and z of the probability that the origin is connected to x, y, which is a neighbor at the origin, is connected to z, and the origin is not connected to y. Okay? This was the thing that we said is up to constants, the same thing as the derivative. Okay? So, how are we going to do that? Well, we'll use this coupling, right? So we said, okay, this is the probability that x is in k, z is in k tilde y, minus the probability that this happens but this doesn't happen. But z is not connected to y. Or, sorry. Let me just write the whole thing. Okay, this is valid because this event actually contains this one. Okay. All right. So clearly, if I just take this, it's just equal to the product, right? Because these are just defined to be independent configurations. Okay. So if I just sum this first term, I just get the square of the susceptibility. So in other words, okay, up to some factors of p and 1 minus p that I've been ignoring, you get that this is its square minus this sum, which is more complicated. So again, this is that we get the configuration that we want in the independent clusters, but it goes wrong, and we just copy that again. Okay. But again, how does it go wrong? Well, it goes wrong like this, right? It must be that in these independent clusters, I see what I want. The origin is connected to x. Y is connected to z, but this cluster also comes and cuts off actually every path from y to z in this independent cluster. I should say, by the way, one thing I've been glossing over a bit, there's always a possibility whenever you do these diagrams and so on, that these vertices could actually be equal to one of the zero, like x, y, or z, right? It might be, for example, that this tree actually is just a path that goes from x to y to z. That's actually fine. It doesn't cause any problems. It's good to worry about that kind of edge case because it could cause problems, but in fact it doesn't. There's of course a similar thing where this path could this cluster could intersect this path at y, which actually causes like a different problem here. But in any case, in both cases, you must have that this cluster intersects this path. Yep.
But how are the three binary?
What's that?
How are the trees binary? Is it the same?
Oh, you mean here? I mean, really, this is some big cluster, right? It's just
No, but above for the tree graph inequalities.
Oh yeah. Yeah, you're right that you do get these non-binary trees, but it's actually just the case where the two vertices in the binary tree are equal to each other, which is fine because when we do the sums, we don't restrict the vertices to be distinct. Okay, yeah. Yeah, like when you look at the 3-point function, there's a contribution from when these two internal vertices are actually the same vertex, which gives you a tree of degree 4, but it's already included. It just comes from that equality case in the sum. Okay, so now we have to bound this, right? But the point is, this is actually a situation where we can apply BK. Okay? So of course it's a little bit different because we have these two independent configurations, but basically we can sum over, essentially we have y, whatever this point, again, these could be highly non-unique, but there's some point in the where y is connected to A, is connected to Z, disjointly, and this other cluster is connected to X. And if I look at this path to where it intersects here, again, I can do this trick of looking at the last place the two paths intersect. So I get this point B. And so what I have is in this cluster, I have independent connections y to A to Z. And in this cluster, I have independent connections from the origin to B, from B to X, and from B to A. Okay? So what I get is that the second sum, so the error, is that okay by the way, or is it too dark? So the error is bounded by, using the BK inequality, I get this sum over, actually let's just use the diagrammatic notation, right? It's I have the origin and I have y. These are my two white vertices. I'm not summing over them. And then I have this picture. Okay? So of course, when I sum over this vertex and this one, I just get two factors of the susceptibility, right? So this is equal to the susceptibility squared times this diagram. Okay, where again these are labeled 0 and y. Okay, so you can see this is very similar to the triangle, except it's not the triangle that closes up and I get the same two values here. I've just gone to the neighbor instead. This is what's called the open triangle. Okay. Now what you can see is that if the open triangle is strictly less than 1, right, so the bound that we've proven is actually that the derivative, again up to these p and 1 minus p factors I've been ignoring, and is bounded below by 1 minus the open triangle of the susceptibility squared. Okay? So if you know not just that the triangle condition holds, which means this sum is finite, but you know something stronger, which is that this open triangle, where this is a neighbor at the origin, if that's actually strictly less than 1, then that actually establishes this complementary differential inequality. Okay, so you can see this is actually quite an easy consequence of these BK type ideas. And again, really what we did here to get this is we used inclusion-exclusion, or more accurately, the Bonferroni inequality, which means just expanding inclusion-exclusion to the first negative term and using that as a lower bound. Okay. Now, of course, you know, what I said before is that if the triangle is finite, then that is enough, in fact, to get a differential inequality like this. And all I want to say about that is that the proof is very similar, it's just more annoying to do properly. So the point basically is that what you first show is that if the triangle is finite, then you can find a value of y, some point y, maybe not a neighbor at the origin, that makes this small, makes it less than 1. Okay? And then you say, okay, well, you know, my derivative was about neighbors at the origin, not about points, some other fixed point. But you can say up to some constants by forcing some edges to be open and so on. You can say it's comparable to if I took y to be any other fixed point, not necessarily a neighbor at the origin. And then you can get it that way. And you know, the fact that if the sum is finite when you do the diagonal one, then you can find a y that makes it small. This is a sort of basic Fourier analysis fact, basically. It's something about positive definite matrices. It's nothing really to do with percolation. It's like the Riemann-Lebesgue lemma or something like that. Yeah.
So you don't need to push this inclusion, exclusion to further correction to get that. It's a different...
Yeah, that's not... Right, right. Yeah, indeed. You can do it that way. It's much more difficult, but you'll get more precise results. So, you know, in the lace expansion, and also you wouldn't be just deriving it as a consequence of the triangle condition. You would be part of a, doing the whole lace expansion. So if you do that, you can actually get not just the order at the derivative, but to show there's actually a constant so that it's asymptotic to that specific constant times the square, where this constant will encode all these microscopic interactions of the two clusters. And that comes ultimately from doing something like an infinite order inclusion-exclusion. But you don't need to do that just to get the correct order. Okay. But this version where the open triangle is small, this gives you the main idea. And then the pushing this to just handle finite triangle is just technical stuff that's not really that interesting. Okay. Good. Okay. So I opened this section with a promise that I was going to explain why dimension 6 is important in percolation. So let's see a first answer to that question now, and I'm going to iteratively give you answers that I hope you find increasingly convincing. Okay, so we just saw, I was just telling you how this triangle being finite is sufficient for mean field behavior. Okay, now we also know that or believe, let's say at this point, that mean field behavior ought to be characterized by this Green's function like decay of the two-point function. So like mean field should imply that this is of order x minus y to minus d plus 2. Okay? And then you can just check that if you form the triangle but with this value, okay, this is finite if and only if d is larger than 6. Okay? That's something easy to check. You can imagine if x and y, if you pick both of them uniformly at random on a ball of radius r, or well, basically you'll have r to the 2D choices of such points, and a generic choice of those 2 points will give you, all of these will be of order r, so you'll get r to the minus 3D plus 6. So if you just look at that contribution from like generic choices of x and y on a given scale, this will be r to the 6 minus d, which indeed decays with the scale when d is bigger than 6, and it grows when d is less than 6. Of course, if you want to really show this is finite, you need to be a bit more careful than that, but that's the main idea. Okay. Now, of course, you might find this argument for y, at least it's a first argument you can do where 6 appears as a relevant value, right? That's a good sign. But you might complain, okay, well, you've only showed that this is a sufficient condition for mean field behavior. It's actually an interesting open problem, by the way, whether the mean field exponents imply the triangle is finite. That's actually not known. So it's only a sufficient condition, but you know, this is a first answer, and we'll see more soon. Okay. Good. So what do I want to say next? Okay. Maybe before moving on, let me tell you a... Yeah. Sorry, can you say that again?
Does it happen only in dimension 6?
In dimension larger than 6. Yeah. So 6 is the critical dimension. So when D exceeds dimension 6, you'll get this mean field behavior. And that we can actually prove with some caveats that I discussed earlier. In D equals 6, you expect to have almost mean field behavior with these logarithmic corrections that we don't know how to prove yet. And then in strictly lower than 6 dimensions, you should get something really different. Let me give you, before moving on, let me give you an alternative explanation of this, of essentially the same answer, which maybe I won't write too much actually, but let me give you the oral version of it. So there's a general phenomenon that if you have some a-dimensional random object, whatever that means, and a b-dimensional random object, and they're both in d-dimensional space, then they'll intersect each other a lot exactly when a plus b is at least d. Okay, so let me give you a few examples of this. So if you should always think of a random walk as somehow wanting to be a two-dimensional object in some sense. Okay, so a point is a zero-dimensional object, right? And this gives you this a way of seeing, perhaps not the most convincing way of seeing, but why 2 is the critical dimension for random walk being recurrent or transient, right? It's saying, does a random walk typically intersect a point? Well, it does it exactly when 2 plus 0 is smaller than d, right? You could also ask, as we were talking about earlier, when do two random walks intersect each other infinitely often? Well, each random walk is a two-dimensional object, so there's 2 plus 2, the critical dimension for that is 4. Right? You could also ask, when does a random walk tend to intersect a line? Right? Well, a line is a one-dimensional object, random walk is 2, so it will be 2 plus 3 is 3. 2 plus 1 is 3, sorry. So, okay. How can you see percolation in the same vein? Well, what you see when you do this coupling, right? What we said is we first sample the cluster at the origin, and then we sample the second independent cluster, right? And we want the point is that for the derivative to to have the correct order, it actually is not a problem for these two clusters to intersect a lot. You know, that might be your first guess if you were trying to do this kind of argument for computing the critical dimension. You might think it should be 8 because, well, these large critical clusters, you should think of them as being 4-dimensional objects. Why is that? Well, in high dimensions, they want to behave like branching random walk. The branching random walk, it's like you have this random tree, which turns out to be a 2-dimensional object. That's not obvious to see, but let's just take it as a given. And then you're embedding that random walk using, that random tree using random walks, which doubles its dimension because the random walk has this square root type scaling of its displacement. So when you take this 2-dimensional random tree and then you embed it into space using random walks, it becomes a 4-dimensional object. Okay? And so percolation clusters in high dimensions, they want to look like critical branching random walks, so they want to be 4-dimensional somehow. So if you asked, when do two large critical percolation clusters tend to intersect or not, the critical dimension for that will be 8. Okay, but that's not the critical dimension for percolation. The critical dimension is 6. And the reason why is when you analyze this coupling, you actually don't care if these two clusters intersect. The only thing that matters, as we saw in this computation, is whether this cluster intersects the path between these two marked points in the other cluster. Okay? Now, when you only look at that one path, it now becomes a two-dimensional object rather than a four-dimensional one. Essentially, it should look like a random walk in high dimensions. So that's within that sort of calculus of adding together the two dimensions and seeing whether they're less than the ambient dimension. That's how you see that it's 6. It's 4 plus 2. It's a single cluster, a cluster intersecting a path in the other cluster, which is four dimensions for the cluster, 2 dimensions for the path. Okay. So we'll see one more explanation of why the critical dimension is 6. But to do that, I first want to talk about scaling and hyperscaling inequalities. Okay. So or scaling and hyperscaling relations, I should say. Okay, so you know, if you're working in 3 dimensions or something, as I said, it's very unlikely that you'll be able to compute these exponents. They're not expected to have nice, exactly expressible values, but they should satisfy some simple relations between the various exponents. Okay? In fact, I mentioned in 2 dimensions that the way that we actually know the values of all the exponents is really there's just maybe 1 or 2 of these values that you can compute directly from all the SLE machinery, and then the rest of them you get from those values together with the scaling relations, which are actually proven to hold in 2 dimensions by Keston, you know, under the assumption that at least one of the exponents is well defined, something like that. Okay? And the thing is, these scaling relations, they basically just follow from some assumptions that all the distributions that appear are just sort of reasonable functions that have reasonable kinds of scaling behavior. Okay? So an example of this is, you know, we know, or we don't know, but you know, what we would like to be true at criticality, as I said, is that you have something like some power law tail for the cluster at the origin. Okay? So then you can ask, well, what should the corresponding statement be below criticality? Let's say P is now less than PC. Well, one thing I should mention that we do know, and I'll actually prove this at some point. So I mentioned earlier the sharpness of the phase transition, which says that this susceptibility is finite if and only if P is less than PC. And it's actually a consequence of the tree graph inequalities, right, that I get if I look at the kth moment. It satisfies a bound of this form. Well, really, we had the 2k double factorial, but you know that's the same order as this up to changing the constants. Okay, and this implies that if I'm below PC, I actually get an exponential tail bound like this. Okay. Now, one thing I should stress here is that the proof of the sharpness of the phase transition, it just tells you that this is finite. It doesn't give you any control on how this blows up as you approach PC. So you know you get that if P is less than PC, you get these this kind of thing, which is actually equivalent to this. You know, the moments of an exponential random variable grow like a factorial. So you don't get any control on what this constant is. You just know it's positive. But nevertheless, you know that below criticality, you have a very light tail on the cluster volume. Now, what you expect, though, is that if you're very close to criticality, Well, you won't be able to tell that you have this light tail until you look at very large values of n, right? I mean, of course, the distributions are going to be very close to each other if p is very close to pc until you get to large values of n. And so it's reasonable to guess that what does this distribution look like? Well, it looks like this power law factor times something like this. Sorry. So you get some constant in the exponential where zeta p is something finite, p less than pc. Okay. Now, in fact, to derive the scaling relations, you don't really need anything as strong as this. You just want to say, what does this distribution look like? It should have roughly some form like this, where g is some kind of very rapidly decaying function. It doesn't really have to be an exponential. Okay? And basically, if you just want to do heuristic theory, you can get quite far and derive all these relationships between critical exponents and so on, just by sort of assuming you have reasonably nice forms for the distribution like this. Okay? So what you should think of this, zeta, this is the typical size of a large cluster. Okay? What I mean by that is, you're subcritical, so eventually it becomes very, very hard to have large clusters, but you don't really feel that until you get to this characteristic size. Okay, so up to then you just see this power law, which is not too difficult to get large clusters. Okay? Now, what you expect, again, it's natural to just posit that this, again, has a power law, right? And I should stress, again, with all of these things, I'll talk a lot about computing these exponents and so on, but it's in many cases an equally difficult problem to show that the exponents exist. Okay, so this is always just a heuristic thing, just saying, okay, there probably should be some power law. Eventually we'll get to proving some theorems, but let's just say this blows up like some power of how far you are from the critical point. Okay? And this exponent is called the gap exponent, for reasons that will become more clear later. Okay. So let's suppose that you knew that you had a reasonably nice functional form for your volume tail away from criticality like this. Well, if you did, you can actually derive relationships between the different exponents. Okay? So, for example, let's say you look at the susceptibility. Right? Well, of course, that's just summing the volume tail, right? In general, for any random integer valued random variable, the expectation is the same thing as summing the tails from 1. Right? Which we're saying is roughly like n to the minus 1 over delta times this some rapidly decaying function n over zeta of p. Okay? Now, a general phenomenon when you have a sum like this, and this is not difficult to justify if you have a specific function like an exponential, is that roughly speaking, you should just truncate the sum when this starts to get small, right? This will get small when n is of order zeta p. Okay? So roughly, this is the same as just taking this polynomial term, but truncating the sum at zeta p. Okay? Which, of course, you can compute what this is. It's zeta p to the 1 minus 1 over delta. Or it would be more convenient to write this as delta minus 1 over delta. Okay? So in particular, if you believe that everything is described by these power law exponents in this way, what you'll get is that, well, this is supposed to be like P minus PC to the minus gamma, right? And I get that it's equal, or roughly the same, as P minus PC to the minus delta times big delta times small delta minus 1 over delta. Okay, so this gives me one of the scaling relations, which is this. Okay, again, this is not at all a proof, and in general, we don't know that these exponents are even well defined or anything like that. But as a heuristic, this is sort of clearly should work. Yeah.
Just, I think for P less than PC, usually the prefactor n in front is more given by Ornstein-Zernike type of Gaussian correction.
Well, that's for the...
If you really apply it within the range of zeta, then it's what you want, which...
Yeah, well, okay, so one thing about that, of course, this is for the volume tail, whereas Ornstein-Zernike is for 2-point, right?
It's
Maybe there's something...
Yeah,
but there's also something where, even for the 2-point function, these Ornstein-Zernike asymptotics, they appear on much larger scales than the correlation length, so they're actually not relevant for these kind of computations.
That's the point. You truncate at the correlation length, so that's why you don't see them, but instead the other factor, I guess.
Yeah, indeed. Yep. Yeah, I think Gordon Slade has been working recently on trying to explain this transition between the two different scaling regimes in a lot of detail. Okay, so that's one relation we can get this way. Now, of course, this is completely heuristic, but what you can see is that the tree graph inequalities actually give us a kind of inequality version of this picture, which is sharp in high dimensions. Let me bring down. So the tree graph inequalities right, so we saw that this kth moment is bounded by 2p minus 3 double factorial times the first moment to the 2p minus 1. Okay, and it turns out you can package this inequality nicely by looking at the expectation of the size of the cluster at the origin times e to the, let's say, lambda times the cluster at the origin. Okay, and if you just take the Taylor expansion of the exponential and plug in these estimates, what you get is that this is bounded by the first moment times 1 minus 2 lambda expectation, the first moment squared to the minus 1/2. Okay, hopefully you'll just believe me that that computation works out if you do the Taylor expansion and then plug this in. Okay, this is for lambda less than 1 over twice this square. Okay, and in particular, you can use this to get the tail estimates that the probability the cluster at the origin has size at least n is bounded by square root e over n times e to the minus n over 2 expectation squared. Okay, so what you can see is that this inequality that you get from tree graph It actually looks very much like this kind of assumed form that we took to derive the scaling relation. Of course, it's only an inequality, and it has this root n that should only be the correct thing in high dimensions. But one thing you see here is that the role of this typical large size of a cluster is played here by the square of the second moment. Okay? And again, this is something where that's only the correct order, again, in high dimensions. Right? But this inequality is always true, and it's kind of an inequality version of this kind of ansatz formula that we expect to be true in any dimension. Okay. Good. Okay. All right. So another point I want to make about this picture is everything we discussed here there are similar versions. Again, this is only a heuristic anyway, so it's not like I really proved anything, but the similar versions should hold for, e.g., P equals PC, but cluster is in a finite box. Okay? So, you know, if by working in a finite box, I'll also make all the moments and so on finite again, and I'll give things a nice tail. And there should be a similar effect where, you know, this zeta is now depending on the side length of the box rather than on how subcritical I am. But I should get something very similar, that within a finite box, there'll be some typical size of a large cluster. You should have very rapid decay of the tail when you go above that typical large size. And when you compute moments, they'll mostly come from clusters that have that order. Okay? So, by the way, another thing you could have done here, sorry, let me put this other board up. I may still want to read that. Okay? Another thing we could have done here is look at the higher moments, right? So you can do exactly the same computation, right? But look at some k at least 1. And what you would get is that, well, this will be like the sum, but where I have an n to the k minus 1 over delta. Right? In general, to get the kth moment, I need to sum the volume tail times the power k, n to the k minus 1, times some constant as well, but let's ignore that. Right? Which would give you zeta to the k minus 1, sorry, just k minus 1 over delta. Okay? Or the way I'll write that is this characteristic size to the k minus 1 times the first moment. Okay, so that's one way. That's one way you can see what this characteristic size should be. And again, that will be true whether you're taking p less than pc and making it subcritical, or working within a finite box. This characteristic large size should arise as the ratio of the second moment to the first moment. Okay. So one interesting open problem. Is it always true? So you should imagine, you know, this is interesting in 3 dimensions, for example, that the kth moment is always of the same order as the ratio of the second moment to the first moment to the power k minus 1 times the first moment. Okay? So if you have the validity of this kind of ansatz thing, then that will be true. That's something that just comes out from this, right? This zeta p exactly is the ratio of the second moment to the first moment. We actually don't know that this is always true. You know, it's always true in every case that we've been able to analyze, and it should always be true. But this is something where maybe there is just a nice general argument that doesn't require you to, prove anything too serious about the actual exponents or anything like that. Okay. This is, of course, related to your question earlier about whether you can do improved versions of the tree graph inequality that include the high moments. And the answer is you can, but they don't get you all the way to this. Okay. Good. Okay. So in particular, this gap exponent should describe how much the moments increase when you go from first to second, or second to third, third to fourth, and so on, which I guess is why it's called the gap exponent, although I'm not completely sure about the etymology of that. Okay. So before I move on, so one further comment about this. Again, you should think of this as like an inequality version of this kind of scaling hypothesis that always holds. We'll actually see some other inequality versions of that later on, which actually are sharp in low dimensions too. So in some sense, we can get quite close now to proving things that look kind of like this, although they're certainly not strong enough to actually derive the full scaling relations. Okay. Okay. Maybe I'll just mention that there are very similar computations you can do regarding the two-point function. In fact, these, if anything, are better known. So if you take p less than pc, what you expect is that you'll have something similar. You'll have whatever the scaling is at criticality times some function which decays very rapidly and again has a characteristic scale. Of course, this is not going to be the same characteristic scale as before because that was a volume and this is a distance. So this one is normally denoted xi of p. And xi of p is known as the correlation length. Okay. So again, at this point, none of these things are actually defined rigorously, and in fact, for many purposes, you understand for the best understanding, one should not stick too closely to the rigorous things. Of course, eventually you want to prove theorems, but one thing is there are actually many inequivalent ways one could define the correlation length, and generally speaking, it's good to sort of switch between them when you need to prove theorems, and ideally you'll be able to prove that they're the same, or the same order, more likely. But basically the idea is when you're below criticality, there should be some scale at which you start to feel the effect of not being critical. Right? And of course, that's very reasonable in here, right? It's basically saying the two-point function looks like the critical one until this ratio becomes order 1. And then once you go above that, this is a very rapidly decaying function, so it will start decaying very rapidly. Yeah, so again, I'm leaving this intentionally vague. As we were saying earlier, in fact, distance is much larger than the correlation length. You actually get a different asymptotic form, the Ornstein-Zernike one, but which has a different power of the distance in it. That is, as far as I know, not relevant to the critical behavior, basically. Okay, and so you can do similar computations using these assumed like ansatz forms of these functions. So, for example, and again, what you expect is that this has some kind of power law growth. The traditional name for this is nu. Okay, and for example, if you look at the susceptibility, well, this is nothing other than the sum of the two-point function, right? Bilinearity of expectation again. So again, using this form, what that means is to get the correct order for this, you should just sum this until you get to the scale, and then the rest of the sum is going to be really small, so just forget about that. So this will be roughly the same as summing x of order at most the correlation length right? Which of course I can write by summing over the distance, like summing over boxes, right? Each box has r to the d minus 1 points in it. Each point contributes r to the minus d plus 2 minus eta. These two d's cancel, and I'm summing this to the correlation length. And this is roughly the correlation length to the 2 minus eta. Okay, so this gives me another one of these scaling relations, which is now gamma equals nu times 2 minus eta. Okay. There are of course more relations you can derive via similar computations. And I guess I do want to stress the general point that even though we're mathematicians and we want to prove things, it's actually very important to understand the heuristic, the non-rigorous ways of doing things first. They often have a lot of the actual content of what's going on in them. Of course, there isn't really any content here. It's just like assuming a reasonable functional form and then seeing the consequences of it, right? There's no like physical intuition really. But still, it's important to know where these things come from and where these basic relationships between these exponents and things, why they should be true. Okay.
Sorry.
Yeah.
So all these relations, it's for ZD any value of D?
Yes, yeah, yeah.
And the open problem is any dimension as well?
Any dimension, yeah.
Okay, it's not mean field.
Yeah, so it's kind of like, it's essentially, okay, this is also an open problem, right, to prove this. But this is a sort of, would be a consequence of this kind of scaling formula. But this is something potentially there is a simple argument for, maybe.
Yes.
Okay. Good. Yeah, and I should say these scaling relations that we just derived heuristically, these were both actually proven by Kasten for two-dimensional models, and he really proves these kind of things as well, these nice functional forms for things. And they're also, of course, true in high dimensions. In that case, we don't really prove them by proving the scaling relations, though. It's just, you know, you compute all the quantities and you see that they do actually satisfy these relations. Okay. All right. By the way, I was advised that maybe it's a good idea to take breaks during the 2 hours, so this might be a natural point, actually. So the next thing I want to talk about is the hyperscaling relations. And basically what these are additional scaling relations that are believed only to hold in low dimensions, so below the critical dimension. Okay? And the basic idea is that there should be a qualitative distinction between high and low dimensions that looks something like the following. So suppose, for example, that you look at a large box with side length n, right? And you say, how many large clusters are in the box? Okay, now of course you have to say what you mean by large, right? Now one particular thing you could mean is crossing clusters. So in other words, clusters that touch two opposite sides of the cube, for example. You could ask for clusters of diameter at least n over 10 or something like that. You know, there are a number of ways you could define what it means for a cluster to be large. It turns out that these won't affect the answers that we get to these questions. Okay, and the basic dichotomy is that when the dimension is large, including at the critical dimension, we have many large clusters. And in dimensions strictly less than the critical dimension, we have order 1. Okay? Now, order 1 here really means a tight number. And, you know, of course, that number, it's a random variable and it will change. So, you know, in particular, if you say clusters of diameter at least epsilon n, you'll get more of them as you make epsilon smaller. But if you fix epsilon to be a constant, then it shouldn't change the asymptotics. Okay? So, in fact, in the specific case where you look at crossing clusters, for example, it's known that for D larger than 6, again, under the assumptions that you can use the Lace expansion that you need to analyze high-dimensional percolation, the number of large clusters is actually n to the d minus 6. You get a polynomial number of large clusters. Okay? Whereas in 6 dimensions, it should be some power of log. I actually haven't memorized this particular power, so I apologize for that. And again, for D smaller than 6, it should be order 1 again.
Why is it ND minus 6? Is it easy to understand?
Yeah, it's... okay, so the way you should think about what's going on in high dimensions is, like we were saying before, the high-dimensional clusters, they kind of want to be 4-dimensional objects. Yes. Okay? So if you look at the biggest cluster in a box, it should have size... Actually, the biggest one will be n to the 4 log n, because there's, you know, you should think each one, it has something like an exponential random size times this n to the 4 scaling. So the bigger... There are polynomially many of them, so the biggest will fluctuate larger by a log factor, but you should think basically there's this soup of large clusters that have volume roughly n to the 4, right? Now, then you say, well, how many of those large clusters are there? Well, we also know that the expected size of the cluster, of the intersection of the cluster at the origin with the box, right? Well, this is just the sum of the 2-point function over the box, right? So it's roughly the same calculation we did before, r to the d minus 1, r to the, let's just say minus d plus 2, which is in high dimensions. Again, these two d's cancel, and you get that this is, so this is up to n, this is n squared, okay? Which is the same as the sum of the Green's function, right? It's the expected time that the random walk spends in the box, okay? Now, what we expect heuristically, and of course in this case you can prove everything really, but let's just do the heuristic version, is that where does this expectation come from? Well, it should be roughly, and actually this is a good way of thinking about what this typical large size means. If you want to compute expectations like this, they should roughly be like the probability the origin is in a large cluster times the size of a large cluster. The size of. Okay? And, you know, similarly, if you looked at the second moment, you should get this probability times the square of this, right? Now, I just said that the size of a large cluster is going to be n to the 4. And of course, this probability, well, it's the number of large clusters over n to the d. Right? And here I get n to the 4. Okay? So if you just rearrange this, you should get the same thing written here, that the number... Oh, wait. Is that right? Sorry.
Okay, because you have n squared on the other side.
Oh, sorry. There should be another n to the 4 here, right? Sorry. The probability the origin is in a large cluster is the total size of all clusters, which is the number times n to the 4 divided by n to d. And then you get an extra n to the 4 from this term. Okay? So you get the number is n to the d plus 2 minus 4 minus 4. But yeah, that's actually a good way of thinking about what these heuristic things mean about like the typical large size of a cluster and so on. It's that these kind of formulas should be true. That, you know, if you want to compute some moments, you basically say, well, the dominant contribution comes from being in one of these typical large clusters, and then you just multiply together the probability of being in one of those and what the contribution is from one of them. Okay. Yes, and by the way, this of course will you can use the same computation to compute what the power of log is here as well, but that's, if you assume the other conjectures. But yeah, actually, one thing I can mention that I find interesting about the conjectures in 6 dimensions is that you know, we had this earlier, this quantity zeta p, which was the typical size of the large clusters when p is less than pc, right? And you know, earlier when I wrote down these conjectures for the log corrections in 6 dimensions, we kept getting 2/7 over and over again. We didn't get it all the time for the 2-point function. It's 1/21. But actually, the underlying reason why you keep getting the same number, that's actually it's a consequence of the conjecture that there is no logarithmic correction for this quantity in 6 dimensions. It's supposed to just be this to the power minus 2. The fact that the reason why you get the same 2/7 appearing in several different places is basically because this power of log is 0, and then that propagates to a number of the other ones being the same. So I find this particular aspect of the conjecture quite curious, just because, you know, in general, if there's something that does not have a log in it, it might be easier to establish or understand why you get that one. And then maybe that would be a good starting point for computing some other logs. But anyway, that's just an aside. I don't.
So that's for d equals 6.
Yeah.
This is the one for d equals 6.
And d bigger than 6 as well.
Okay.
Yeah. Yeah, it's just an interesting thing I wanted to point out, that conjecturally, this quantity does not have a log correction.
I thought there was some log correction for Ising model, but no, maybe not.
So for Ising's, I think something similar happens, that the 2-point function is not expected to have a log correction at the critical dimension. And then, you know, it's just helpful that at least one of the things doesn't have a log. I mean, again, maybe you can compute that one first. Okay. Anyway, this is just an aside.
About this number of crossing clusters, all
Yeah.
these statements are conjectural, or
The high-dimensional ones are proven. Yeah, so I should say the high-dimensional, again, subject to the usual caveats about the high-dimensional results. That was done by Michael Eisenman, I think in the 80s or the 90s. I guess his result was conditional on these things about the 2-point function and so on that were only proven afterwards. Actually, that paper is published in a nuclear physics journal for some reason. Last time I saw him, he told me he was going to tell me the story for how that happened, but he didn't, so anyway.
For small dimension, it's known only for dimension 2, or?
Yeah, indeed. So of course, there's not much known in 3, 4, 5 dimensions. One interesting thing I'd say here is I'm about to talk about the hyperscaling relations, which are basically additional scaling relations that come from this assumption, which is sort of like you're fixing the value for one exponent in some sense, and then deriving additional relations from that fixed value. And it is actually known. There's a paper, I think by, I apologize if I get this wrong, but I think it's Borges, Chase, Keston, there might be another author. They show that if you assume this is true in a sufficiently strong sense in any dimension, then you can derive all these consequences, like the relationships between all the other different exponents from this assumption. But of course, we don't know how to prove that for low-dimensional nearest neighbor models. This is one of the things that I will be telling you how we can prove versions of these hyperscaling things and this whole trichotomy here in the long-range models. Okay. So the hyperscaling relations, so if the number of large clusters is order 1, we can deduce additional relations between exponents. Okay, so again, I'm continuing to do all this non-rigorous stuff, and I promise at some point I will start proving theorems, but let's continue to do things non-rigorously for now. Okay, so here's an example. Suppose I just want to look at the two-point function. Right, so this is this probability that x is connected to y. Okay? Now, what we think should be true is that if you're below the critical dimension, then essentially at this scale, like the difference, the scale being the distance between x and y, there should be order 1 of these large clusters, and basically whatever quantities I'm interested in computing, their contribution should come from just these order 1 large clusters. So this should be roughly the same as saying that x and y both belong to the typical large cluster at scale their difference. Okay? Which should be the same as the probability basically that x is connected to distance at least x minus y over 4, say, and y is also connected to this distance. Okay? Now, of course, these two events are independent, right? Because this one depends only on the edges inside this box, this one only on these edges. So this should be roughly like the square of this probability that x is connected to the boundary of this box of side length x minus y over 4. Okay? So if I introduce another critical exponent, right? So this is called the one-arm exponents. And the traditional notation for this is 1 over rho. Okay, so one example of these hyperscaling relations would be that minus d plus 2 minus eta, which is the two-point exponent, should be equal to 2 over rho, minus 2 over rho. One thing you'll see, by the way, is quite often these the scaling relations don't tend to involve d, whereas the hyperscaling relations do. Okay, so again, this is something that should only be true in low dimensions. Right? In high dimensions, this equality is actually not true at all. So what happens in high dimensions, it's actually a theorem of Cosma and Nachmius, that this one-arm probability, the probability the origins connected to distance r, decays like 1 over r squared, right? Whereas this is like r to the minus d plus 2, right? So you see, again, those two exponents, they actually are equal when d equals 6, but this becomes, this two-point connection probability becomes strictly less likely than both of them connecting to the boundary of the box when you go to more than 6 dimensions. Okay, but this should be true in low dimensions. Okay. Okay. Now, okay. So, moreover, if we define another exponent df by saying that the largest cluster in the box of side length n has size roughly n to the df, so this is like the fractal dimension of the large cluster, if you like, that's why it's df, okay? Then, you should also have, under these hyperscaling type assumptions, saying, okay, there's only order 1 large clusters and they determine everything interesting, this one-arm probability, well, it should just be equal to the probability that the origin is in a large cluster, where again, large means this typical largest size, this typical large size on scale n, which is like the size of this cluster divided by the size of the box. Okay? So if you rewrite this scaling relation in terms of df, you get minus d plus 2 minus eta is 2 df minus 2d, which of course you can rearrange to 2 minus eta equals 2 df minus d. Okay, so of course there are more hyperscaling relations you can derive. The point always being that basically this assumption that you have a single or order 1 large clusters at a given scale and that these determine everything interesting is kind of fixing the value of one exponent, and then you're getting more equalities from doing that. Okay, so the third answer is that d equals 6 is the unique dimension where the mean field exponents satisfy the hyperscaling relations. Okay, so for example, if you look at this equality here, right, we saw that, what we said is that in high dimensions, the fractal dimension of these clusters will be 4, right? So, and eta will be 0, right? So if I look at 2 minus 0 equals 2 times 4 minus d, right, and then I get d is equal to 8 minus 2. Okay. So this is another way that you can see that the critical dimension should be 6. Okay. Now, of course, actually at the critical dimension itself, you don't really expect to have this order 1 number of large clusters, but you expect to only have a polylog number. So in terms of actually determining the exponents, all the arguments will go through. It's just there'll be some additional log factors floating around. Okay, so I think this is a fairly convincing explanation of why 6 is the critical dimension. It does still have some problems, right? So for one thing is that, I think it's pretty plausible that, you might have a critical dimension above which this number of large clusters ceases to be order 1 and starts becoming large. It's unclear why this should be the same critical dimension as when you switch between having mean field behavior and not, right? In fact, that is what happens, and it's kind of reasonable that, once you have a lot of large clusters in a box, they start to become sort of weakly interacting with each other, which is what should lead to this mean field exponents. But it's certainly not completely clear that these two different changes in behavior should always be simultaneous with each other.
It's not a rigorous explanation.
Well, in the end, what we can do is like prove theorems, right? And the theorems will, if you can prove things about low dimensions, as we will be able to, by the way, for the long-range models, they will eventually, you will see that you do indeed have a different behavior according to whether the dimension is bigger than or larger than this thing that it should be. But I guess my view is that these heuristic arguments are better. They give you a better understanding than the rigorous arguments do into why6, for example. And not that we can. So actually, we can prove various things that are like. It cannot be when you're below 6 dimensions, you cannot have all the exponents take their mean field values. It's just inconsistent. And so that is there are rigorous things like that. The trouble with some of these things is it's possible like some of the exponents take mean field values and some don't, things like that. Yeah. So actually, one of the things that we'll talk about next week is that some of these estimates that I've been writing down, talking about the hyperscaling relations, many of these things have inequality versions that we can prove. Okay, and basically, the thing about these inequality versions is that they're true actually in general dimension. It's just that they're only the correct order in low dimensions. Okay, and that's similar to the tree graph inequalities. They're also true in all dimensions, but they're only the correct order in high dimensions. So we can actually prove some inequalities. In both cases, we have inequalities that are true always, but they're only sharp in one of the two cases. Okay, and these in particular can tell you that it can't be that all the exponents take their mean field values when you're strictly lower than 6 dimensions. Okay. All right, I'm almost out of time for today. Let me see if there's anything I want to say quickly. Yeah, this is probably a good time to just stop for today, so I hope you don't mind ending early.
We had already 4 hours. Are there any questions? I was wondering, is this explanation for the Ising model, let's say in the FK representation, will there be the same thing also, one cluster below and the critical value, or it's typically percolation?
I would guess so. I might be wrong about that, though. I don't know these things so well in that context. It tends to be. I mean, one thing you have with of course, with the FK Ising is that, like when you do this relationship, for example, these two smaller boxes wouldn't be independent anymore. So it's unclear whether even if you made this assumption that you could derive consequences in the same way. Yeah, I'm not completely sure. I'm sure there'll be something analogous, but I don't know if it's the same thing in terms of the clusters, especially the clusters in the FK representation. I mean, often that's not the most useful representation to use for critical Ising. Yeah.
If we work with other graphs than ZD that have finite dimension, like transitive graphs of polynomial growth or stuff like that, there are all other geometries than ZD, but do they satisfy the same relations? Do they have lattice expansion?
Yeah.
I mean, lattice expansion or techniques to...
Yeah, so I'd expect basically all this stuff is true for those graphs. In terms of the lattice expansion, Gadi Cosma has... yeah, it's like, he says he knows how to do it for polynomial growth. And I don't know if the paper will ever appear.
And the stuff of Panis and the Luminil Copain, doesn't it? Don't they have something relying on its kernel estimate or something?
Yeah, I think they do a lot of stuff with half spaces in their new approach, which is harder to push to the more general context. Yeah, I think for the polynomial growth, my understanding is that in the for dummies the lace expansion for dummies paper, they have this way of doing the lace expansion that uses the Edgeworth expansion, which is like a asymptotic expansion for the lattice Green's function. And they have some note there that they have a more complicated way of doing it that only uses the local limit theorem. And then this would suffice for the generalizations. But actually, since that paper appeared, there have been papers that just prove Edgeworth expansions for nilpotent, for polynomial growth transitive graphs. So it's unclear whether you even need this other argument that they had. I mean, probably you can just run their argument with the Edgeworth expansion.
Thank you. If there are no more questions, we might stop here. Let me remind you that the next lecture is at EHES Monday, Tuesday, Wednesday, Friday, 10 o'clock in the morning. So thanks again, Tom.
Yeah, thank you.